Thank you, Mr. Nitin. Now that we have entered the domain of IIT Mumbai, let's continue on that journey. And this time we have Mr. Praveenkumar from IIT Mumbai. He'll be presenting his works on effect of particle type Carboxyl graphene-coated carbon fiber via electrophoretic deposition on mechanical properties of epoxy composites. Over to you, Mr. Praveen. Yes.
Good afternoon, all of you. I'm Praveenkumar Jatothu. I'm a PhD scholar from IIT Bombay. I'm doing a PhD from Center for Research in Nanotechnology and Science Department. And working under Professor Aparna Singh, Metallurgical Engineering and Material Science Department. So I'm going to present here is the topic of effect of particle type carboxyl graphene, carbon coated on the carbon fiber via electrophoretic deposition technique and their mechanical properties. Yeah. So first I will present what is the motivation for this work and introduction and literature survey related to this and objectives of my study and material used for the study, experimental methodology and results and conclusions. So motivation is that we have various advantages of carbon fiber reinforced polymer composites. They have high specific strength and stiffness properties, and carbon fiber shows high strength properties compared to other fibers. But which lacks, there is these carbon fibers subjected to mechanical loads, they will fail at the interface region. That could be due to the chemically inactive nature of the carbon fiber surface, that is due to the turbostatic structure of the carbon fiber. If you see that figure, the bottom left corner, that graphite structure you could see, and the graphite structure are basal planes present at the surface of the carbon fiber, and this is chemically inactive in nature. So this cannot bond with the epoxies easily. So the material fails at this region because there is a lag in chemical bonding here. So if you see the system of the any single fiber and epoxy, so there are three major constituents. One is the fiber and epoxy, and at the interface region there is one more region will be formed, that is the interface region. That will be formed because of the adsorption of the polymer chains at the surface of the carbon fiber and the entanglement of these polymer chains, and that will have some thickness. So the major strength comes because of the load transfers from the epoxy to the carbon fiber. If this interface strength is higher, then there is a load transformation from the carbon epoxy to the fiber will be higher. So this is the major region to get the higher mechanical properties. So epoxy compared to other resins, epoxy shows the highest mechanical properties, and carbon fibers we know the mechanical properties. So to increase the interfacial strength, these are the theories are available. One is the mechanical interlocking theory, which is that if we add any graphene or any fillers to the interface region, that will create the friction. Because of that, there will be increase in the mechanical properties. One more is the chemical bonding. If you treat the fiber surfaces, that will form the chemical bond and increase the strength of the composite. And one more is that transition layer T. Here, the interface has the variation in the modulus. So if it is a lesser flexible modulus, then stress concentration will be reduced because of the deformation of the interface region. If it is a higher modulus, and that transfers the load from the epoxy to carbon fiber easily. And infiltration theory is that the epoxy should infiltrate to the carbon fiber, and it should wet completely to the fiber. Then only we achieve the better mechanical properties. So based on these theories, various researchers are available. So many have done the oxidation treatment on the carbon fiber and coatings and sizing and chemical grafting and multi-structural depositions. And out of these, one thing is that graphene deposition on the graphene increases the surface roughness, and which increases the thickness of the interface region, and which create the mechanical interlocking and modulation in the transition region. So we know that graphene has very good properties such as electrical and mechanical properties. These are nowadays graphene available in various forms like graphene oxide and carboxyl graphene. So these graphene without having any functional group, they cannot disperse into the any medium like such as water. So we need some other functional groups such as oxide functional groups, hydroxyl and carboxyl groups. So majorly I use carboxyl graphene in my study. So how this graphene can be deposited on the carbon fiber. So various deposition techniques are available. One is the spray coating and dip coating and electrophoretic deposition. Electrophoretic deposition is that which has electrolytic cell and the one dispersion medium that will have graphene fillers, and there are two electrodes and oppositely charged. When we supply the potential to this electrode, there is a movement of these particles toward the opposite charged electrodes, and they will get deposited onto the electrode. So Hamakers predicted the mass of deposition of the graphene particles, such as any other filler particles, onto the opposite charged electrode. If you have a particular electrophoretic cell and which has a particular amount of dispersion medium and a constant surface area of the electrodes, and the major variables are the voltage and current and concentration of the fillers into the dispersion medium. So EPD cells are available in various forms, so we can deposit on a particular electrode, and we can at a time multiple fabrics also we can deposit, and it is also we can deposit in a continuous form also. So graphene has such as graphene oxide, when we disperse in a liquid medium, that dissociates. For example, if it has the carboxyl graphene, which has GCOOH functional groups, when we disperse into the water, it dissociates COO minus and H plus ions. So, which will give the negative charge to the graphene. Purely, if we disperse into the dispersion medium and we subject to the EPD, that is subject to the opposite charges, there is a lesser amount of deposition. If we modify the charges of the graphene, previously it will have negative charge. If we modify with any charge modifier such as the magnesium nitrate, and these are some of the salts that can modify the charge of the graphene. So I use the magnesium nitrate to modify the charge. So if we modify the charge, that negative charge of graphene converts into positive charge, and we supply the now we convert it into positive charge, and now if we supply the charges to the electrode, that will move towards the negative charge electrode. So these are the reactions at the anode and cathode. During the graphene deposition, magnesium charges react with the carboxyl graphene groups at the edges, and that will form COOMg that we can see at the right corner, and that will be deposited. Where magnesium charges move faster along with the graphene particles and deposited at the carbon fiber. Here, along with the graphene particle, there is a deposition of magnesium hydroxide, and that supports the graphene platelets and the carbon fiber. So here, the objective is that preparation of stable collider solution and optimization of VPD process parameters such as voltage, current, and concentration, and the study the mechanical properties of these composites. The material used are these carboxyl graphene polyacrylonitrile based carbon fiber and DGEB epoxy resin. So experimental method is that we first disperse the magnesium nitrate into the DI water, and we subject it to ultrasonication, and after that we disperse graphene carboxyl to that dispersion medium, and we do the probe sonication. Along with the ultrasonication, we do the EPD. After the EPD, we use that fabrics to make the composite. So this is the weight percent calculation. So we deposited two weight percentages. One is the 0.13 weight percent and 0.45 weight percent. So here 0.13 weight percent is film type deposition, and 0.45 is the particle type deposition. And left side we can see the pure carboxyl graphene. So after deposition, we could see the increase in the functional groups such as hydroxyl carboxyl functional groups. And Raman test gives that there is an increase in the disorderness. That may be because of the sp2 hybridization of graphene converted into sp3 hybridization, and that because of the formation of epoxide and hydroxyl groups under the graphene. EDS analysis shows that there is increase in the interfacial thickness. So these are the composites. First one is a PCF, pristine carbon fiber composite, and 0.458% deposited composite and 1.38% deposited composite. So 1.38% deposited composites shows some of the voids. That may be because of the obstruction of the graphene particles during the infusion of the epoxy using VRTM method. So tensile properties shows the 0.45% shows the highest mechanical properties, such as 62% increase in the tensile strength, and there is a 12% increase in the modulus. Whereas the tensile strength increase in the 1.38%, also there is a decrease in the modulus. That may be due to the voids. So here increase in the tensile properties due to the increase in the interfacial strength and mechanical interlocking and chemical bonding. So these are the SEM micrographs. So here we can see the pristine carbon fiber composites. There is after failure, these are the images. So there is a debonding at the epoxy and carbon fiber, but there is no debonding and addition of the epoxy to the carbon fiber in the case of graphene deposited composites. So these are the failure mechanisms that pristine. There is an increase in the interfacial thickness, and if you see the transverse failure, there is first epoxy debonds with the carbon fiber, and that after that carbon fiber will fail. But after deposition of the graphene, there is addition of the formation of thicker interface and addition of the graphene particles. So this is the same, and there is the interfacial failure in this case of graphene deposited. So flexural properties, there is improvement in the flexural properties also for the case of 0.4 weight% deposition. So film type 1.3 weight% deposition shows less flexuration because of the voids. this is the institute flexural test. So first, in the case of pristine composite, that is A figure, there is a formation of fracture. Is a fourth one, and that is propagated through delamination to the center, and that fractured finally. So if you see the B figure, this is 0.48% deposited, but there is a formation of the fracture at the right side, but that is not propagated because of the obstruction of the graphene, crack obstruction of the graphene. There is a crushing failure at the center of the composite. But whereas in the 1.08% deposit, there are voids. Fracture starts from the voids here. So these are the SEM images. From these images, we can see that pristine case, there are delaminations and fiber pull-ups, more fiber pull-ups. And here fibers are fractured in the shear manner. Whereas in the case of 0.458% deposited, there are crushing failure in compression side and less fiber pull-outs in the tensile side. So this is the failure mechanism. Here fibers fractured in the shear manner, but in the case of 0.48% deposited, there is a crushing failure and fibers fractured in the transverse direction. The ILSS property shows there is a decrease in the ILSS properties compared to pristine case. That may be because of the voids. So we have found the void percentages using computed tomography. So we got 0.004% in the pristine case, but 1.23 and there is higher voids in the case of film 1.3 deposited. So the flexural properties are affected and ILSS properties are affected because of these voids. But these voids can be reduced if you fabricated using autoclave method. So in that we can increase the temperature so that the viscosity get decreased, and there may be a better infiltration of the epoxy at the graphene cluster of the graphene, so the voids can be reduced. So come to the conclusion. So there is an increase in the interfacial strength because of addition of the graphene particles, and there is an increase in the mechanical properties to the around 62%, and flexural properties also. There are some void formation in the composites that can be reduced with the fabrication, changing the fabrication methods such as autoclave methods. So my special thanks to my Professor Aparna Singh, the mechanical department, metallurgical and material science department, and thank you since 2024, and thank you for IIT Bombay, and thank you for Ahmedabad University. And thank you everyone. And if you have any questions, you can ask. So we have 2 published papers on this work and 2 patents. If you have any collaboration, if you want, you can contact with these mails. How? Yes.
Is there issue when vibrations or
Yes.
there a problem, then it will debond.
Yes.
How you can avoid in that condition? Because all the tests you have done may be static condition.
So here, pristine case, this is the pristine case when we apply the mechanical load such as flexural load. So this will compress on the top side, and there is a change in the mechanical properties of epoxy and carbon fiber.